Hey friends, I thought it would be helpful for us to walk through this study guide together to finish out chapter 14. So this video will be dedicated to doing just that. Here we go. Okay, so here we have part one of the study guide, and what we're going to do is just use the words in the word bank to fill in the blanks as needed. Air is a blank of oxygen gas dissolved in nitrogen gas. Well, air is a solution of oxygen gas dissolved in nitrogen gas. So we'll put solution right there. The oxygen in the air is the solute. Solute. There's less oxygen than nitrogen, so oxygen acts as the solute, and nitrogen is the solvent. Because oxygen gas dissolves in a solvent, oxygen gas is a soluble substance. Soluble substance. How's it going? Good? Good. A substance that does not dissolve is insoluble. Insoluble. Blank solutions are the most common type of solutions. Liquid solutions are the most common type of solutions. If one liquid is soluble in another liquid, such as acetic acid and water, the two liquids are miscible. Miscible. Sometimes in class we pronounce it mixable to help you remember, mixable, but miscible. Miscible is the actual pronunciation of that. However, if one liquid is insoluble in another, the liquids are immiscible. An example of immiscible, you'd have oil and water, right? That's an example of an immiscible mixture. All right, we're going to move on to the next section. Okay, in this part, we see a diagram of sodium and chloride in a chunk together, sodium chloride particles in a chunk, and then the sodium ions and chloride ions being separated. Hydration is solvation in which the solvent is water. What is solvation? We said that solvation is the separating, I'm just going to write the two words here, separating and surrounding. It's up to you to remember what I'm talking about, but the separating and surrounding of solute particles by solvent particles. The separating and surrounding of solute particles by solvent particles. So here we see the solute particles, sodium and chloride, being surrounded by, in this case, water is the solvent, and so water molecules are separating them and surrounding them. So the next page, number 10, as sodium chloride dissolves in water, what happens to the sodium and chloride ions? Well, they are separated and surrounded by water molecules. All right. The next question, explain the orientation of the water molecules around the sodium ions and chloride ions. Let's look back at the diagram in question, and you'll see my words are following there. Sorry about that. But remember that these water molecules have an attraction to the sodium ions and chloride ions. But notice that around the chloride ions, and you might recall this from our video, the water molecules have the oxygens pointed away from the chloride ions, and then they have the oxygen molecules pointed toward the sodium ions. And the reason we said was that in these water molecules you have polarity. And on one end of the water molecule you have a slightly negative end, that's the oxygen end, and then on the hydrogen end you'd have the slightly positive end. It's designated right here right here in this diagram, you see positives on the hydrogen, negatives on the oxygen. Again, we're not talking ionic here. We're just saying that there's a slight positive field on the hydrogen end and a slight negative field on the oxygen end. So, to answer the question, let's go back. So, the oxygens, the slightly negative, there we go, slightly negative oxygens face the positively charged sodium ions. Writing is getting bad here, sorry. And the slightly positive hydrogens, you guys are probably writing faster than I am, face the negatively charged chloride ions. Chloride. All right, so there you go. There's a definite negative and positive thing that's happening here, and a natural attractiveness that takes place. How does the strength of the attraction between water molecules and sodium and chloride ions compare with the strength of the attraction between the sodium ions and chloride ions? Well, it has to be greater, doesn't it? The water molecules have a greater attractiveness to those sodium ions and chloride ions than the sodium ions and chloride ions do to each other. I don't know how you're going to write this down, but you just need to understand this concept. Let me say it again. The water molecules have a greater attractiveness to the sodium ions and chloride ions than the sodium ions and chloride ions do to each other. And the reason why we know this is because there's actual solvation that occurs, isn't there? The water molecules do indeed separate and surround the sodium ions and chloride ions. If there wasn't an attractive force great enough to do that, it wouldn't happen. So therefore, the water molecules must have greater attractiveness than the sodium ions and chloride ions do to each other. Make sense? Okay. List 3 ways that the rate of solvation may be increased. Remember video 3, I think it was? We have 3 things. What are they? Agitation, surface area, and temperature. That is raising any one of these. All right? Raise the agitation, stir. Raise the surface area, use powdered sugar instead of cube sugar. Raise temperature, put it on some heat. Right? So those 3 things. Agitation, raising the agitation, raising the surface area, raising the temperature. Increasing any one of those and you get better solvation. Okay. Do a little true or not true here. True or false? The overall energy change that occurs when a solution forms is called the heat of solution. That's true. All right. True or false? Number 15, solubility is a measure of the minimum amount of solute that dissolves in a given amount of solvent at a specified temperature and pressure. That's false. One word is the problem. Right here. It's the maximum amount. Easy for me to say. Maximum amount of solute. All right? So solvation occurs, number 16. Solvation continues as long as the solvation rate is less than the crystallization rate. Is that true or false? That's false. Solvation continues as long as the solvation rate is greater than the crystallization rate. If the crystallization rate were greater, you would just have supersaturation, where it just kept crystallizing. You couldn't get any more in there. All right? In a saturated solution, solvation and crystallization are in equilibrium. Yes, that's true. In other words, the rate of solvation is the same as the rate of crystallization. It's just a kind of a back and forth thing that happens. Number 18, additional solute can be dissolved in an unsaturated solution. Yes, that's exactly what that means. We can put more solute in a solution that still has, we could think of, it still has room for solute to be dissolved, right? In an unsaturated solution. Then finally, number 19, the solubility of a gas dissolved in a liquid decreases as the temperature of the solution increases. That's true, yes. That's exactly right. Now, a little side note. Thought this might be interesting to you. For those of you that like to fish, you ever wondered why when you throw your line out there that you usually try to hit an area where there's not a whole lot of sun beating down, or it may be kind of a more shady area? The reason is because those fish like to hang out in the cooler water. Why? Because more oxygen is dissolved in that water. It's easier for them to get their oxygen through their gills in areas where the water's slightly cooler. We're not talking about frigid, obviously, but slightly cooler because there's more oxygen in that water. And they can get their oxygen and they can just relax and chill out. Sorry, I had to say it. But that's the reason why you don't find them a whole lot in the hotter portions of the water. Okay? There you go, your fishing tip for the day. All right, let's move on to the next page. Okay, this is section 2 of your study guide. By the way, just a reminder, for some reason the study guide doesn't exactly match the book in terms of sections, but we're getting it all done, so it doesn't really matter, does it? Section 2, here we go. We've got a table here, and in this table we have mass. We're going to do percent by mass with this section, percent by volume with these solutions. In solutions 1 through 4, we have a combination of sodium chloride and water. In solutions 5 through 8, we have a combination of ethanol and water, 2 liquids, of course. It says data related to aqueous solutions of sodium chloride and aqueous solutions of ethanol are provided in the table below. Use the table to answer the following questions. Circle the letter of the choice that best answers the question. I love circling. It's a whole lot easier than writing. I'm just saying. Okay, what is the percent by mass of NaCl in solution 1? So this solution right here, 3 grams of solute, 100 grams of solvent. And remember what percent by mass is. I'm going to write it right over here. Percent by mass is the mass of the solute over the mass of the solution. Now, by the way, remember, and that's, by the way, times 100. Should I say by the way one more time? By the way? Okay. Incidentally, the solution is the solute and solvent. Important to remember as we make these calculations. All right, I'm blind now. You happy? I'm blind. All right, so percent by mass of NaCl. Yes, I'm starting to get my vision back. So solution 1, 3, is it just 3 divided by 100 times 100? No. 3 divided by 100 plus 3, solute and solvent combined. So 3 divided by 103 times 100. I'll just do it right here. 3 divided by 103 times 100, and that actually gives you 2.9%. So those of you that said B, way to go. Give yourself a pat on the back if you can do that, because sometimes it's really hard to do that. All right. I'm going to erase this if you don't mind. Even if you do mind, it's too late. Which of the following solutions is the most dilute? Is it solution 1, 2, 3, or 4? Well, it's fairly obvious, I think, that it's solution 4 because you have 3 grams of solute, the same amount of solute, but I have a whole lot more water, don't you? Right? So our percent by mass is going to be a whole lot smaller there. So solution number 4 is the most dilute. Recall the terms: dilute, concentrated. Dilute, less solute, more solvent. Concentrated, more solute. So the higher the solute content, the higher the concentration. What is the percent by volume, now we're using the other side, of ethanol in solution 5? Solution 5, this one right here. And again, percent by volume is the same way as percent by mass. Percent by volume, volume, is the volume of solute, in this case the ethanol, over the volume of solution times 100. Okay. And again, the solution is the solute and solvent combined. All right. That's real important for you to get in your noggins, okay? Because later on, we talk about molarity, molality. It's important, okay? So 2, right, divided by 102 times 100. Solute divided by solute and solvent combined. So 2 divided by 102 times 100. That's actually 1.96. It's not too exactly, but because of rounding, it's 2. I know. I'm hurt by it too. But they only gave us these answers to respond to, so that's what we have to do. It's 1.96. Just remember it's a little bit less. Here, I'll write it right here. 1.96%. Okay? All right. Which of the following solutions is the most concentrated? So the opposite of what we had number 2. Most concentrated solution? Solution 8. Right. We've got 15 grams of solute here, 100 grams of solvent. That's roughly like 13%. 13% by volume, okay? So there we go, solution 8. Okay? So that does it for that section. We'll move on to the next one. Bottom half of the page now. In your textbook, read about molarity, or you can just watch the incredible video from earlier. And preparing molar solutions. Read the following problem and then answer the questions. Well, that's what we're here to do. An 85 milliliter aqueous solution, which means it's dissolved in what? Water, right. Aqueous solution contains 7.54 grams iron 2 chloride. Again, the Roman numeral 2 means that here iron has a +2 charge. Calculate the molarity of the solution. All right, so they take you very much step by step. These are going to seem like softball questions, but there's a reason for it, and they're taking you step by step on how to do this. All right, so what's the mass of the solute? Well, of course, it's given to us right here, 7.54 grams of iron 2 chloride. What is the volume of the solution? The solution, 85 milliliters, 85.0 ml, okay, milliliters. Write the equation that's used to calculate molarity. All right, step by step, like we said. Molarity equals, if I like to do it one over the other, so you can write it however you want, but moles of solute divided by liters of solution solution. All right, moles of solute divided by liters of solution. That's molarity. In what unit must the amount of the solute be expressed to calculate molarity? It's a fancy way of saying, what units are you going to use? Moles. Moles. Moles of solute. In what unit, now we know what's going on, don't we, for number 9. In what unit must the volume of the solution be expressed to calculate molarity? Liters. Liters. Number 10, write the expression needed to convert the volume of the solution given in the problem to the volume needed to calculate the molarity. Okay, so here's where we start to make our calculations. We need to convert, right? Because we have milliliters of volume and we need liters. So how do we do that? We're going to use a little dimensional analysis here. 85.0 milliliters. And I'm going to use a conversion factor. It's milliliters to liters. Right? 1 liter equals 1,000 milliliters. By the way, if you want, you can go ahead and solve it here. We are going to solve it on the next page. Okay, what quantity must be used to convert the mass of the solute given in the problem to the amount of solute needed to calculate molarity? Well, that would be the molar mass, wouldn't it? The molar mass of what? The molar mass of iron 2 chloride, FeCl2. All right? Now, write the expression used to calculate the amount of solute. I'm going to use a little dimensional analysis again. It said our amount was 7.54 grams. And I need to calculate the moles instead of grams. So I'm going to put moles on top. 1 mole of FeCl dose. And I'm going to put grams on the bottom. Now I'm going to figure out how many. So I'm going to use my periodic table that's in the back. So that's why I'm looking to the back here. And 126.75. All right. So now grams cancel. I'm left with moles. That's awesome. That's what I want. And so I get. Oh wait, no, we're gonna solve that down here. I forgot. They just want the expression. They just want the expression. All right. So that's good for right there. Now calculate the molarity of the solution. Show all of your work. Calculate the molarity. Here we go. Molarity. 85 milliliters first. We're gonna work the same direction they did. They did volume first. Fine. We'll do volume first also. So 1 liter, 1,000 milliliters. So that gives us 0.085 liters of solution. All right? So far, so good. Now let's figure out the top, the moles. 7.54 grams FeCl2. 1 mole of FeCl2 over 126.75 grams of FeCl2. Grams cancels. I'll give you a second if you want to compute this. Time's up. Okay. 0.0595 moles of solute. Cool? Cool. Now we just got to do molarity. Molarity, molarity. Again, moles of solute, liters of solution. All right, liters of solution. So I have 0.0595 moles in 0.085 liters of solution. Oh, well, that's nice of them. Okay, so that gives us 0.7 moles per liter. Or we can also say 0.700 molar. You don't have to underline the M. I'm just underlining it to show you we can use the units in that fashion. Okay? Now, one more question before I move the page. Give me a minute to move the page. How does molality differ from molarity? Molality is equal to moles of solute per kilogram of solvent. Not solution, solvent. So you're kind of taking the two parts of the solution and comparing them instead of one part compared to the whole solution. Molarity, of course, we've just discovered, well, no, we already knew it, but is moles of solute per liter of solution. And those are the differences between the two. All right? Molality, moles of solute per kilogram of solvent. Molarity, moles of solute per liter of solution. Time to move the page. Okay. Calculate the molality, not molarity, but molality, of a solution of 15.4 grams of sodium bromide dissolved in 125 grams of water. Show all of your work. Right. Challenge accepted. 15.4 grams of sodium bromide. Never. All right? So we're going to find the number of moles of that because I'll put it over here. Molality, moles of solute per kilogram solvent. All right? Remember, understanding the concepts and the units means so much. It gives you direction. It really does. So I know I have to find moles first here. So 1 mole of never over, I gotta compute grams here. Hang on. Give me just a second. Okay, I got 23 and all right, so we got 102, I'm gonna say 102.89. Yeah, good enough. 102.89. 102.89. All right. So I got my setup here. I have grams canceling there. I get out my calculator. Not really, but I get out my calculator, and that's going to give me 0.15 moles of NaBr. All right. So now let's do the bottom. Kilograms of solvent. They tell us in the problem we have 125 grams of water. 125 grams H2O. Let's find the kilograms. Let's find how many kilograms that would be. So we have grams on bottom, right? We want grams on bottom, kilograms on top. What's the relationship? Well, 1 kilogram equals 1,000 grams. Grams cancels. And I'm left with 0.125 kilograms. Okay? And now I just make the computation for molality. Molality equals 0.150 moles over 0.125 kilograms. Okay? So my molality here is 1.20 moles per kilogram. Or if you can get it, it's hard to say. It really is hard. Molol. See? You try it. Go ahead. See? It's hard, isn't it? Molol. Okay. Anyway, molality. All right? What is mole fraction? Mole fraction was when you have the ratio of the number of moles of solute. I'll write it this way. Mole fraction, this is the symbol we use. is the ratio of moles of solute over the moles of solute plus the moles of solvent in a solution. I had to make the dash longer. Okay? Moles of solute in a solution over the total number of moles of solute and solvent. That's what mole fraction is. Calculate the mole fraction of HCl in an aqueous solution, so it's dissolved in, right, water, that contains 33.6% HCl by mass. Oh no, percent, what are we going to do? Come on, you know this. We convert to grams, don't we? We pretend like we have 100 grams of this stuff. So 33.6% means we have 33.6 grams of, we'll say, hydrogen chloride dissolved in, what's the rest? 100 minus 66.4, good. 66.4 grams of water. Again, the two of these combined add up to 100. Here's one part, here's the other part. We're just going to figure out moles of each one, right? That's what we need for mole fraction. So we have 1 mole HCl, and grams of HCl, we got 1 plus 35.45. We'll just round it for now. I'm a little tired. 36.5 grams HCl. All right? And that's going to give us, wow, like 0.92, something like that. Let me here make sure. Okay, yeah, 0.92, not bad. 0.92 moles HCl. Sorry for the splice there, but 18.02 grams per mole. That gives us 3.68 moles of water. And so now all we have to do is use our mole fraction equation here. So we have moles of solute. So this is a mole fraction of HCl. Moles of solute, 0.92. Moles of solute and solvent, 0.92 plus 3.68. That gives us 0.92 divided by 4.60. Wow, that's really kind of them. All right, so our answer is 0.200. By the way, remember, mole fraction is a dimensionless amount. It doesn't have any units attached to it, so it's just 0.2. And what's the mole fraction of water in this case? It's 0.8, isn't it? Because it's a fraction of the whole. If this represents 0.2 of our whole, then water must be the rest. 0.8. 0.2 and 0.8 give us 1. All right, guys, that's the first two sections. I'm going to do a separate video so you don't have one long, huge video. Separate video on sections 3 and 4. See ya.